All right, welcome to lesson 2-6. Today we're looking at the derivatives of exponential and logarithmic functions. So this lesson is really going to be split up into two different parts. First, we're going to start on logarithmic functions, and then we'll move on to exponential functions. So you're going to notice that for the most part, I'm going to tend to focus a lot on the natural log function here. And that's because in calculus, the derivatives involving natural log tend to be the easiest. And traditionally, that's what the AP exam focused on. However, in the last couple of years, College Board has really moved toward an expectation that you are actually familiar with logs and exponentials of all bases, not just base e. So, in this lesson, you're going to see me address the log of any base and the exponential function with any base, and I would strongly recommend that you work toward memorizing those as well. Okay, so the derivative of the natural log of x turns out to just be 1 over x. Now, that seems pretty simple, and it is. Oftentimes, however, we are going to not just have natural log of x. This is oftentimes going to be an inner function, so we'll have to use the chain rule. So oftentimes it's going to really be like a natural log of u, and we'll just have to apply the chain rule in that situation. Okay, in general though, so what if I'm not just dealing with log base e, which is what natural log is? What if I have log of any base a? Well, that derivative is just going to be 1 over x still. But this time we also multiply by the natural log of a, which is the base. Now notice that that natural log of a that we're multiplying by, that's in the denominator. So as you're trying to work to memorizing this, please don't accidentally move this out to the side or on the top. It is x times the natural log of a, all in the denominator. And if you think about it, remember natural log, this is really log base e. And if I were to apply this general rule to the natural log function, this would be 1 over x times the natural log of e. But the natural log of e, hopefully you remember, is 1, which does give us 1 over x. So this general form does really work for all versions of log, not just log base a other than natural log. Okay, so let's go ahead and take a look at a few examples, and then we'll move on. All right, so let's go ahead and start here with example A. F of x equals natural log of the x squared plus 9x. So as you can hopefully see, this is a composition of functions. This outer function is y equals the natural log of u, but u equals x squared plus 9x. So when we find the derivative of f prime, or when we find f prime, sorry about that, we're going to have the derivative of the natural log of u, so that's going to be 1 over u, times the derivative of u, which is x squared, the derivative of x squared plus 9x. Okay, so that's now going to turn into 1 over u times, so of course the derivative of x squared plus 9x does give us 2x plus 9. And I'm going to do two things to finish this off here. So first, of course, I'm going to replace that u back with x squared plus 9x. And I'm going to move this 2x plus 9 up into the numerator because it's really just multiplying with that 1. So finally, we just get 2x plus 9 over x squared plus 9x. And that's our derivative. Okay, moving on to example B. Very similar to what we just did, however, there are two differences. One is, of course, we're not dealing with the natural log. We do have log base 3, so we are going to have to use that general rule. Remember, that just involves multiplying by the natural log of 3 in the denominator. But also, not only is this a composition of functions, but our u, which is the sine of 5x, is also a composition of functions. So it's like one of those examples where we have the nested chain rule, so we're just going to have to do the chain rule a couple of times here. So hopefully you recognize that our y is log base 3 of u, where u is the sine of 5x. But again, we should recognize that the sine of 5x is really a composition of functions in itself. So this is going to be written as the sine of v, where v is 5x. So of course that means to find the derivative of g. So to find g prime of x, we need to find the derivative of y with respect to u. So the derivative of log base 3 of u, remember that's going to be 1 over u times the natural log of 3, because it's a natural log of our base, times the derivative of u. So the derivative of sine of v is just going to be cosine of v, times the derivative of v with respect to x, which is just going to be 5. All right, so now we just have to substitute back in for our u and our v and simplify, clean things up just a little bit. So this is going to turn into, so let's see, that's going to be 5 times the cosine of v, which is really sine of 5, sorry, v is 5x. So I have 5 cosine of 5x over, remember our u is the sine of 5x. But then that still is getting multiplied by the natural log of 3. All right, so we could really stop here. We could clean this up just a little bit. Remember, we have cosine over sine, and they have the same argument. So remember, cosine of theta over sine of theta, that's really cotangent of theta. So I really could write this as 5 over the natural log of 3 cotangent of 5x. So I could write our answer that way as well. All right, so hopefully not too bad so far. Let's take a look at one more example here. All right, so this time we have y equals the natural log of x times x squared plus 1 quantity squared all over the square root of 2x cubed minus 1. Okay, whoa, let's pump the brakes here a little bit. So if I were trying to do the same approach I just did on the previous examples, notice that this is the natural log of u, but our u is a quotient, but within that quotient, we're going to have a product rule. Within that product rule, we're going to have a chain rule. And in the denominator, I also have another chain rule as well. So what the heck? Clearly, we are not expected to just go crazy with all the amount of work on this one. There's got to be something else we can do. And there is. And it's something that you learned back in Math 3 that's going to come in handy a lot right here. And that is properties of logarithms. And I'm guessing a lot of you have forgotten them, so here's a quick reminder. All right, so here are the properties of logs. So remember, if you have log base b of x times y, so if you have the log of a product, that becomes the sum of the separate logs. If you have the log of a quotient, that becomes the difference of the two logs. Notice it's the log of the numerator minus the log of the denominator. Has to be that order. And then finally, if you have log of a power, so log of an argument to a power, remember that that power can move out in front. So these three log properties, which you should already know, but again, I know that a lot of you are probably rusty on it, so I would strongly recommend that you work toward memorizing it. Flashcards, whatever you need. So these three properties are going to save us a lot of time and trouble on this example that I just presented. So let's go ahead and take a look at that example one more time. Okay, so again, in this case, first thing I notice is this is the log of a quotient, because first and foremost, I see that I have something over something else. So the first thing I'm going to do is rewrite this as y equals. Now notice this is still y. I am not putting y prime yet because I'm not yet finding the derivative. I'm just trying to rewrite this log expression using log properties. I'm expanding it using log properties because that's going to then allow us to find the derivative term by term. Okay, so remember the log of a quotient is the log of the numerator, so that's the log of x times x squared plus 1 quantity squared, minus the log, or in this case the natural log, of the denominator, which is the square root of 2x cubed minus 1. Okay, so already that's looking a lot better, but there's a lot more that we can still do that's still going to make this easier on us. So next, I notice that I have the log of a product. So that's going to expand to become the natural log of x plus the natural log of x squared plus 1 squared. And then don't forget minus the natural log of, and just like everything else we've done, as soon as I see a radical, I'm going to rewrite that as a fraction power. So this is the natural log of 2x cubed minus 1 to the 1/2. So this is, again, looking so much better than that original expression. But there's still one more thing we can do here, and that is moving these powers out in front. So finally, I'm going to get y equals the natural log of x plus 2 times the natural log of x squared plus 1 minus 1/2 times the natural log of 2x cubed minus 1. And this is the function that we're going to find the derivative of. And it's going to be so much easier than trying to tackle this original function. All right, so now we can find the derivative. So we get y prime equals, so the derivative of natural log of x, that is literally as easy as it could ever get. That's just going to be 1 over x plus. So now I have 2 times the natural log of x squared plus 1. That's going to be another little chain rule here, isn't it? So this is just going to be 2 times, so the derivative of natural log of u, so this is going to be 1 over u. So sorry, let me go ahead and mention here that u, or y, equals the natural log of u, and u equals x squared plus 1. So this is going to be 1 over u times the derivative of u. All right. Minus 1/2 times, same thing here. This is now going to be 1/2 times the natural log of, let's say v. I don't want to use u again. And then v is actually going to be 2x cubed minus 1. So this is going to be 1 over v times the derivative of v. All right, so I get y prime equals 1 over x plus, so this is going to be 2 times 1 over, so our u, remember, was x squared plus 1, times the derivative of x squared plus 1, which is 2x, minus 1/2 times, okay, so 1 over v, so that's 1 over 2x cubed minus 1, times the derivative of v, which is going to be 6x squared. All right, now we just got to clean this up just a little bit. So I'm going to put y prime equals, so I have 1 over x plus. Now in the numerator, I'm going to be multiplying the 2, the 1, and the 2x, and that's going to just give me a 4x over x squared plus 1 minus, now here, this 2 in the denominator is going to divide with the 6 in the numerator. That 6 is going to knock down to a 3, and then I can multiply the 1's and the 3x squared all across the top. I'm going to get 3x squared in the numerator and a 2x cubed minus 1 in the denominator. Okay, now, yes, technically we could get a common denominator and combine all of this into a single fraction expression. And depending on what we're doing with this derivative, we may have to do that. However, we are just practicing finding the derivative involving log expressions or log functions, so we are going to stop right here. So on any future quizzes or tests where I'm just assessing you on finding the derivative of logs, when, not if, when you have a question that looks kind of like this, please do not try to deal with that as a massive chain rule. Okay, make sure you're using those log properties to expand it as much as you can, and then you can find the derivative term by term. And when you get to this answer, please do not spend any unnecessary time trying to combine this into a single fraction answer unless I specifically ask you to, or unless I specifically ask you to do something with this derivative where you have to do that. Okay. All right, so again, this is the importance of knowing those log properties so that you can expand an expression like the function you had here on part C. All right, and so now that you've already learned about implicit differentiation and now that we've learned about log derivatives, now we're going to combine those. So here we are going to find dy dx, so find the derivative of y with respect to x for natural log of x times y plus 4x squared equals 3. So remember, first thing we're going to do, let me go ahead and rewrite this. So I have the natural log of xy plus 4x squared equals 3. And so remember, first thing we're going to do is we're going to find the derivative with respect to x of both sides. All right, so here I have the derivative with respect to x of the natural log of xy. So again, this is a chain rule within implicit differentiation. So the derivative of natural log of xy, this is going to be 1 over xy times the derivative with respect to x of the product x times y. Plus, all right, the derivative with respect to x of 4x squared, that's just going to be 8x, equals, and then the derivative of 3, of course, is just 0. Okay, so far, we still have to deal with this product rule right here. So I have 1 over xy times, okay, so now the derivative of x times y, so that's the first times the derivative of the second, which is just dy dx, plus the second times the derivative of the first, but the derivative of x with respect to x is just 1. And then plus 8x equals 0. All right, so now I need to distribute this 1 over xy into the parentheses, into each term. So that's going to become, now 1 over xy times x, those x's are going to cancel out. And I'm just going to get 1 over y times dy dx plus, and then 1 over xy times y, those y's are going to cancel out. And I'm just going to get this 1 over x, and then plus 8x equals 0. Okay, so now, remember, I have to isolate the dy dx. So we're going to subtract the 1 over x and subtract the 8x. So now I'm going to have 1 over y dy dx equals negative 1 over x minus 8x. And then finally, I can multiply both sides by a y. And finally, we're going to end up with dy dx equals, that's a negative y over x minus 8xy. All right, so that is implicit differentiation. That just happens to involve a natural log function. Okay, so that wraps it up for the log function section. Let's move on to exponentials. Okay, so again, keep in mind you do need to memorize these. So here we go. The derivative of e to the x, are you ready for this one? Derivative of e to the x is e to the x. So, and just like you saw with the natural log, chances are this is not going to just be an e to the x. This is most likely going to be e to the u. We're going to have some inner function here. So, of course, you'll have to use the chain rule. But yes, the derivative of e to the x is as simple as just being e to the x. Now, that is, I just want to point this out. This isn't a huge thing that you need to worry about. But again, it's just kind of an interesting relationship to think about. So if you think about e to the x, remember that's just another specific exponential function whose graph looks something like this. But remember, this is telling you that the slope of the tangent line at any given point is actually just the same as the y-coordinate of the graph at that point. So it's sort of an interesting relationship that the graph has to its own slope. So that's really what this derivative is saying. Okay, now in general, so what if I'm not just dealing with base e? Like I said, this is something that the AP exam in particular has really started pushing a lot more for in the last couple of years to make sure that you know how to find the derivative of an exponential function with any base, not just base e. So in this case, this is now going to be a to the x, so again, same idea, but now it's times the natural log of a. Okay, and again, if you think about this, if the base were e, this would still say a e to the x times the natural log of e, but the natural log of e is just 1. So you're going to end up with e to the x. Okay, so again, if you're feeling overwhelmed with how much you're trying to memorize, then I would suggest just memorizing this general formula. And then that way, if you get an e to the x, it's going to still work out for you. All right, so let's go ahead and look at several examples involving exponential functions. Okay, so here we go. So we're going to differentiate. So f of x equals 2 to the tangent of x cubed. So again, this is an exponential function, which we know because the base of the exponent is a constant, and the exponent itself is a function of x. So, of course, this does not just say 2 to the x, it's more than an x, so this is going to be another chain rule. And in fact, our inside function, tangent of x cubed, is also a composition of functions. So once again, we have this nested chain rule situation. So this is really going to say y equals 2 to the u, where u is tangent of x cubed, but that's really tangent of v, and then our v is x cubed. Okay, so that means to find the derivative here, f prime of x equals, so the derivative of 2 to the u, remember that's going to just be 2 to the u times the natural log of 2 times the derivative of u. So the derivative of tangent of v is going to be secant squared of v times the derivative of x to the third, which is just 3x squared. So now we're just going to reorder some things and replace the u's and the v's, so everything is back in terms of x. So we get f prime of x equals, so let's see, I'm going to move this 3x squared out in front. and this natural log of 2, which is a constant. This is now times 2 to the u, but remember that's tangent of x cubed. And then times secant squared of v, but remember v is x cubed. All right, and there's not really a great particular order for this one, so this is sufficient. All right, next one. So this one's going to actually combine both the log derivative and the exponential derivative that we just looked at. So once again, hopefully you recognize that this is really a y equals natural log of u, where u is e to the x plus e to the negative x. But because this doesn't just say e to the x on the second one, this is actually another composition of functions. We're going to have a tiny little chain rule right there. So this is really the same as e to the x plus e to the v. Well, let me back up on that one. So we are going to have to use the chain rule, but just on this part within that. So let's address that when we get to that part. All right, so now to find the derivative, we're going to have y prime equals, so the derivative of y with respect to u, that's going to be 1 over u times the derivative of u. So here I'm just going to go ahead and show that we're going to take the derivative of u. Okay, so now that's going to, of course, become y prime equals 1 over, so that's e to the x plus e to the negative x, times. Now, to find the derivative of e to the x plus e to the negative x, remember, that's just finding the derivative of each term separately. Well, the derivative of e to the x, that's just going to be e to the x. Plus, now here, the derivative of e to the negative x, that's where we're going to have another tiny little chain rule. This is going to be e to the u, so e to the negative x, times the derivative of negative x. Again, that's because this was not just an x. But the derivative of negative x is just a negative 1. So what happens is we end up getting y prime equals 1 over e to the x plus e to the negative x times, now here this is going to become e to the x minus, because of the negative 1, e to the negative x. And then finally, when I multiply that with the numerator, we finally just get y prime equals, so we have e to the x minus e to the negative x all over e to the x plus e to the negative x. All right, and that is the derivative of that particular function. Okay, and just to wrap this one up, let's also take a look at an example using implicit differentiation that involves an exponential function. So once again, we're going to have the derivative of y equals e to the xy with respect to x. So first thing I need to do is find the derivative with respect to x of both sides. So I have d dx of y equals d dx of e to the xy. All right, so the derivative of y with respect to x, of course, is just dy dx. Now here, so this is, again, another chain rule with implicit differentiation. So the derivative of e to the u is e to the u times the derivative with respect to x of u. But that's now a product rule. So this is going to be dy dx equals e to the xy times, okay, so the derivative of x times y, that's going to be the first times the derivative of the second plus the second times the derivative of the first. But the derivative of x, again, is just 1. So now we get dy dx equals e to the xy times the quantity x dy dx plus y. Now, you might think that we're done because this says dy dx equals, but remember, you're not done solving until all of the dy dx's are on one side. And right now we have another one sitting in here. So we're not quite done yet. So now I need to distribute this e to the xy. So now it's going to look like this. Dy dx equals, so I'm going to have x times e to the xy dy dx plus y times e to the xy. So now I need to go ahead and move this to the other side so I can get all of my dy dx's on one side. Let me go ahead and move up here. So now I'm going to have dy dx minus x times e to the xy, dy dx, and that's going to still equal y times e to the xy. All right, on the left side, we can go ahead and factor out that dy dx. Of course, that's now going to leave us with a 1 minus x times e to the xy equals y times e to the xy. And then finally, we can divide both sides by this quantity, 1 minus x e to the xy, and we get dy dx equals, all right, so we have y e to the xy all over 1 minus x e to the xy. And that is our derivative with respect to x. Okay, so not a lot that was actually new in this particular lesson. You were just now introduced to two more derivative rules, similar to how you had to find the derivative of sine, which is just cosine of x. So it's kind of along those lines. So it's just memorizing a few more derivative formulas. So once again, we had the derivative of logs and the derivative of exponential functions. All right, good luck.